Let's get started. So, hello, good day. I'm Sidney. I'm from a company called Atlassian. So you might have heard of Jira, Confluence, HipChat, Bitbucket. We kind of make those things. And today I'm talking about immutable data stores and CQRS. So over the past couple of years, we've had a few teams sort of invest a lot in event sourcing, immutable data, and more recently in command query responsibility segregation. We've got various systems in various stages of production. Today is mostly around a particular case study on rewriting a core part of our identity platform to use these technologies. And that's currently in internal dogfooding, and we're currently building up the production scale of it this year. So I guess one of the things we found while we're doing this work was that there's a lot of material, high-level material about event sourcing and CQRS, but not a lot of detail about, like design principles and concrete examples in the real world. And I guess hopefully by sharing some of our experiences today, I'm hoping to sort of fill that gap a little bit. So a quick show of hands, who here is really into event sourcing and CQRS, like using it all the time? Oh, great, good count. Who here is kind of interested in it but hasn't had the opportunity yet to dig into it? Excellent. And who here doesn't really know much about event sourcing and CQRS? Oh, you guys are experts, excellent. Alrighty, so today's talk I've broken up into 4 parts. So first, I'll talk about the what and the why, or really it's how to sell this to your boss, right? And then we're talking about the architecture, so how we evolved from event sourcing into full-blown CQRS. We'll then dig into some code, so we'll walk through some of the event sourcing library that we've written up. And then we'll get into some of the design principles that we've learned along the way. So just a quick intro to event sourcing, just so we're all on the same page. In a traditional application, you've got database tables, and when you have records and when you update those records, you sort of make changes to them in place, right? So that's your master of the data, right? You don't really store history, but that's kind of just how we do things. With event sourcing, rather than having this as our master, we actually store a series of immutable business level events as our master, right? And when to get the original view of the data, we essentially replay these events in series to our original view of the data, all right? So a couple things to note. Firstly, the structure of this event table essentially is pretty simple, right? All we really need is a way of identifying each event uniquely and having them ordered. So hence that sequence column there, all right? In terms of the event payload itself, well, it's just a flexible blob, right? JSON object almost. So all we really need to store it is essentially a key value data store that supports conditional writes to make sure we don't overwrite something that's already there. And the nice thing about having just simple requirements like that is it's really easy to use a database for that, right? You've got Cassandra, you've got Dynamo, you've got all these things that can scale out really, really well. Right? You're not stuck to traditional relational databases, which are harder to scale out. The other nice thing about event sourcing is, well, we replayed one view here, but you can also replay into different database schemas or completely different data stores if you really need to. And we'll see why that's really useful in a minute. All right. So this is a kind of a technical introduction, but what does it mean for a business use case, right? So let's talk about our particular use case we're dealing with. So we're talking identity systems, right? Users, groups, memberships, group memberships and so forth. But specifically, we need to provide different views of this data, all right? So, you might want to search for users, you might want to retrieve by emails, you might want to get users and their group memberships and so forth, all right? But to do that, we need performance, right? So we're talking about high volumes and low latency reads. For us, writes aren't that critical because you don't change things that often, but reads are really important, right? You access that a lot when you log in, when you're getting each page, checking permissions, and so forth, right? And the nice thing about event sourcing is we can provide very customized views for each of these by simply replaying the events into different data stores that is specifically tuned for each particular use case. And we can do that gradually as well. So we can start with, well, let's just put everything in Postgres like we used to do. And then when the scale comes, we can say, well, we have the events now, replay them into Elasticsearch if we need it, right? So we can scale for now and in the future. And that was a really big win for us, for our managers. In terms of other business requirements, well, we had to provide incremental synchronization. So essentially a list of change events for downstream consumers to look at. Well, those are basically the events we're storing. So we get that for free. Nifty. We also get audit trails for free, which again, really critical part of any business system these days. In terms of non-functional requirements, well, one of the big ones obviously is high availability, right? We have to build highly available systems these days. And there's 2 bits of that. One is disaster recovery, and the other is also zero downtime upgrades during normal operation. Now, with disaster recovery, because we have these events, they're immutable, they're pretty easy to copy around between regions around the world, right? And the nice thing is, if we structure our keys correctly, we can actually fail back really easily as well without any risk of overwriting data, which is a bit of a concern. Around zero downtime upgrades. So who here really likes doing SQL table upgrades online? Yeah, no one. I figured that, right? It's dangerous, right? You have nightmares, right? But with event sourcing, it's quite easy, right? Because essentially you have these events. You can bring up your new schema offline, replay the events into there, do your testing, make sure it all works, and when you're happy, you're switching in online, replay lazily the events that you just missed, right? So that's a lot safer than having to, try backups, trying to upload things and make sure it doesn't work, make sure it works and so forth. It's a lot safer for us devs. And this whole replay concept is also really nifty for testing with production-like data as well. So if you want to debug production issues, we'll just replay the events into an offline system until you hit the point where, oh, hang on, that's the bug. All right, well, we can fix it, we can test it and make sure it all works, and then we can apply it in production. So these are, I guess, a mix of technical requirements, but critically, we can actually hit business requirements with event sourcing. And that's a real big win for managers, right? Because they don't care about technical requirements. They want to see business value out of our work. And that's how, I guess, we got support to continue on. So moving on, so how do we actually go about building the system? And you may have noticed that I haven't really talked much about CQRS yet. And the reason is we didn't actually start with CQRS, right? We started with, let's start with event sourcing only, all right? So how did that look for us? We wanted to build a small, sort of monolithic style application. If you imagine that you have a REST call, the data request comes in, goes into our business layer, as it usually does, goes into our data access layer, which in this case would save our events down through event storage wrapper to DynamoDB. Then to read the data out of this, what we'd do is we'd actually pull the event stream straight out of Dynamo, so get a query Dynamo for the stream of events in order. We then accumulate the values in memory, or we can cache them if we need to externally. But essentially, we're folding over that stream, right? So stream of events will come up a lot, and essentially being able to fold over it is one of those nice properties we get. And once we fold over it, we can then return the result back up, the value we want. So this actually works really nice, and we've got production systems working on this. But for our particular use case, the model we started dealing with was getting more and more complex, right? We'd had to join events from multiple streams together, performance-wise and so forth. So that's when we started looking at command query responsibility segregation. So who here is kind of familiar with CQRS? It's a bit of a mix. Okay, good. All right, so a quick intro so we're on the same page. So, when we start with applications, this kind of looks like what we had before, right? Traditional application, you start with CRUD, right? So you have users, you read and write users, right? And most of the logic's dealt with in that domain model. But over time, what ends up happening is we start, building different views of data, right? You want to search for users, you want to get users and group memberships and so forth. And so what typically happens is that the main model gets really cluttered, right? You have optional data fields, you have extra business logic everywhere, just to accommodate this growing and growing domain model. So one of the things that we can do is provide what's called command query separation, right? So having explicit domain models for your write side and your read side, or hence command and query, right? So the command side has a very small data model and has only the rules that it needs to deal with saving a particular user. And then you have a whole bunch of different query views or query models that are targeted to the specific queries that they're supporting, right? So each component is very small, they're independent, devs can work on them independently without having conflict. So if you take this model to the extreme, well, why do you have all this stuff in the same process, right? We can have them completely different services. You can have commands, query services, independent. You can even use different data stores, right? You can save your events in Postgres and then propagate those events asynchronously to different stores like Elasticsearch. All right. So how do we apply this for our system? Well, our first step was to have that command query separation. So we actually had explicit command models and query models. No sharing of case classes or data objects. The only thing they really shared was an event as an API, and I'll talk about that in a minute. Now, the other requirement we had was complex querying, and we're told to use Postgres, so that's fine. How do we get data into Postgres? Well, we then introduced this query synchronizer component, and its job was to be notified whenever events were written. So we started in process with just an in-process Scala Z stream topic. But its job was basically to pull event streams out of Dynamo and process them and push them into Postgres. So this was, I guess, step one into this journey. But we obviously need to get these events out so downstream systems can look at them, right? We don't want to have everything as one big monolith. So what we're doing is we're using DynamoDB streams to get change events out of Dynamo, right, and push those events into Kinesis, which is our event bus. Right? And so we're using either Lambda or some kind of equivalent technology for that. And we can also obviously have multiple consumers now. So you can have the query synchronizer as one consumer. But we'll be building a search service, for example, that might use Elasticsearch. Again, uses the same event stream. And we can also have these other applications downstream listen to that same event stream. So this is kind of where we want to get to as for V1, all right, is what we're currently building. What we really, really want to get to, though, is, well, we have an event bus, but why is this event bus only for this one particular application? What happens if we split our systems into a groups or group memberships application and user profiles and various other kind of identity systems, all right? Why can't we use the same technique and push all our events into that same Kinesis event bus? Then, as an extension to that, well, if we want to expose these events to downstream applications, so your Jira or HipChats or so forth, well, they're external consumers, right? We want to provide them with a stable API. So why don't we transform the internal events, annotate them with extra information or hide away the things we don't want externally exposed and provide them with a different set of events for their external API. So that way we can evolve our internal events from the external events quite differently. So this is kind of where we want to get to over the next year or so. All right, so enough of the pretty pictures. Let's delve into a little bit of code. All right, so I guess when we started this a couple of years ago, we looked around event sourcing libraries, and I guess we didn't see one that really fit the way we coded and the way we deployed our code. So we kind of wrote our own pretty simple one, and we'll walk through that. So the first thing is around how do we model these events. All right, so this is basically how our Dynamo tables look like. All right, so you have a key and a sequence column. So that provides, I guess, a key is, I guess, a unique identifier for event stream. So you might have per user events. So that ID might be your user ID. You have a sequence column, obviously, for providing that ordering. And so an event ID is a combination of a key and a sequence, so type parameters K and S. S has a type class for essentially a 0, gives you a 0, and also the ability to increment, and also the ability to sort between sequences. And the only other thing we have is essentially a flexible value, so some E type parameter. And so our event basically is a tuple of K, S, and E. Pretty simple. All right. So moving up a level, so we then have this event storage API, which this basically wraps around our underlying data stores. So it might be Dynamo, it might be in memory, it could be any other sort of data store we want. It could be a Postgres database if we really wanted to. But all we really need for this to work are three things. Right? So we need obviously a way to save events. So given an event, save it. So F here is just a container type to wrap FX. We also need a way of getting the latest event, and we'll see why in a minute. And we also want to be able to get a stream of events somehow. Now, Scala streams, they're there, but they're kind of pure, right? So we kind of need some sort of effectful stream, right? We want to be able to say, give me query pages of data from Dynamo and return, but make it look like in a stream, right? And luckily, there's this thing called Scala Z Stream, which is now called FS2, which provides exactly just that. And so we use this quite heavily to give us the capability to essentially give us stream-like capabilities, but in an effectful manner, and wrap up all the error handling and resource allocation, that kind of stuff, which is quite nice. All right, so given this event storage, how do we actually use it to save events, right? So saving is a fairly simple logic. So we have this save API case class. Its save function basically goes and gets the latest event out of Dynamo. It will then try to save a new event. So basically what it's trying to do is increment, this thing here increments the sequence number and then tries to save it, right? So if it saves, it's okay, there's no overwrite, all good. If there is a duplicate event, that means there's contention on that database. So obviously, you've got to retry. So retry obviously with some back off, jitter, and sort of a limited retry. And obviously for any other events, or any other errors, you sort of bubble up the errors. So that's pretty much saving events, right? It's pretty simple. But the nice thing is, because you have the sequence number kind of in here, we can actually provide some data constraints, okay? So some level of transactionality, if you like. And the way we model that is through this operation type. So essentially, an operation is a wrapper around a function that says, given an optional sequence number, so it could be optional because you may not have any data in Dynamo, give me an operation result, which essentially means, should I save it, success, or should I not save this event because this condition has failed? And so what we can do is we can write a simple operation things that says, only write this event if a sequence number is at point X, right? And this allows us to expose conditional writes all the way up to our REST API if we want to. So it requires a fairly small change to here. So this is the code you saw before, just spaced out a bit. The big changes would be taking in the operation type, and then essentially applying the old events or old event sequence number to the operation. And then if that succeeds, you save it. If not, reject. Okay? And this gives us ability to save events with some level of constraints on it too. All right, so querying then, okay? So there's two ways of querying here, right? So I guess we started with that pull model, and then there's also kind of a push model where you're listening to events off an event stream or an event bus. So we'll cover both. So firstly, with querying by pulling, right? Remember, we essentially have a stream of events, right? And when we query, we want to essentially say get or query by some query key, type key, give you back some optional value. But because the event store gives us a stream of events, all we really need to do is fold over it, right? Fold over it with some accumulator function. So this accumulator function f, so given an old value and an event, generate a new value that you keep on feeding through. And the nice thing about Scala Z streams, or FS2, is it gives us all this mechanics for you automatically. So what you can do is, given some event stream, you push it through or pipe it through this fold, and then run the whole thing at the end to get your result. And that kind of comes for free. So yeah, it's kind of nifty, that. All right, so the one thing I haven't really covered off is, okay, what's this question mark here, right? Remember, your event store deals with event stream keys only. And it's kind of boring to only query by event stream keys, right? So one other little thing we can do is to say, well, I can query by anything as long as I can get my event stream key out of whatever query parameter I want to provide. All right. So we've all wrapped this up into this query API case class, so you can instantiate that. You're basically passing the functions you need and the event storage, and you could basically get functions like get history, so you can get history. So please only get me values up to 2 days ago, for example. Or you can kind of get a scan of history as well, so you can get snapshots of history over time, which is kind of nice. Again, all that comes for free essentially because we can use Scala Z stream. All right, so moving on to pushing. So this is so I guess where we see this is you have events push to you via this event bus, and again we're using we treat events still as an event stream, right? So Scala Z stream has this thing called a channel, or what's called now a pipe. And that's essentially a way of effectively processing events from your event stream, all right? And so what we can do is we have this query synchronizer, that query synchronizer component. What it does is, given an event stream process, I want to run it through some sort of effectful channel, right? And so this effectful channel is the bit that actually tries to do, write things to Dynamo, or write things to Postgres. And so its logic is pretty simple. Essentially, its first step is, well, can I write? So can I try to increment my Postgres sequence number? So make sure I'm the only one writing to that. And if that succeeds, then you can write, do your insert update statements and so forth. If not, you roll back transaction because someone else has already processed the event, and you can continue. All right, so this is all the query synchronizer is. And to use it, we hook it up to a Kinesis processor, which basically is a wrapper around an AWS sort of Kinesis client library sort of interface, which basically gives you a list of events, or it forces you to have a function that takes a list of events and returns units, so an effectful operation on your events. And so all we need to do is somehow generate those events. So we can either push those events straight from the input, or we can read them from Dynamo. There are some subtleties because why we might want to do that. But once we have those events, then it is just call query synchronizer and just run the thing, right? Now you might be asking, well, why would I bother with this complexity of dealing with Scala Z stream when we're pushing these events through? Well, the reason is, and we'll talk about it a little bit later, is sometimes you actually want to be able to do pulls and pushes for queries, right? So for the primary case, you might want to say, look, let's deal with pushes, asynchronous pushes to your query synchronizers to write to Dynamo or write to Postgres. sometimes you want to say, I want to do a force read and say, well, make sure that my latest version, my Postgres is actually up to the latest events I've seen. Right? There are some cases where you want that consistency. And having it all modeled the same way, using channels and so forth, allows us to choose between them quite easily. All right. So that's code. So let's talk a little bit about design principles, because we talked about events and streams and stuff, but what do they actually look like? So I guess I call them 3.5 design principles. And I think the first one is, okay, what do these events look like? And I guess I call it events as an API, right? And the reason why I say that is when you start designing an API, you think about what consumers want, not what you want to produce, but what consumers want. Okay, what makes it easy for them to consume? And also, what should they be doing, right? You want them to be doing things smartly, like doing things idempotently and so forth. So how do you encourage that in our event design? So it comes down to, I guess, how you structure these events. So there's two general models. So you might have insert update style events versus a set payload style event. All right, so insert update, I mean by, well, when I say I want to insert a user, I have this user added event. And when I do an update of user, I have the separate user updated event, which essentially is a patch, right? So you have optional values and you patch through the values that were changed. And whereas for set events, when you insert a user, you basically have a whole bunch of these set payload events, right? There's no added or inserted keyword. It's just, I'm just setting these values. And similarly, when I when I update this user, I just basically provide yet another set event to overwrite. Right, so there's no distinction between the two cases there. So the insert update case is quite nice from a producer side of things, right? Because that matches the CRUD, that matches CRUD, right? And matches the patch APIs. It's really easy for us to produce events like that. But sorry, the problem is though, there is this now an implicit assumption that there is exactly one insert before any number of updates or deletes. All right, it's not written down, but it's kind of implied, right? And so I guess what we've found is that consumers then say, well, when I see a user added event, I'll just change that into an insert SQL statement, no checks. Similarly, when I do an update statement, I see an update event, I just write update SQL, and that's it, no checks. But there actually are valid cases, depending on how we write these events, where you actually might have multiple insert events, right? And to be honest, doesn't matter. You have ways of resolving it, all right? So you can, if you see duplicate inserts, you can treat the second one as an update. You can just ignore the second one. I mean, there are lots of ways of doing it. You don't have to fail, right? So let's be a bit smart about it. So essentially, we're talking about idempotence, all right? And the nice thing about set events is that because you don't have that implicit assumption there anymore, because you don't know if it's an insert or update, you're forcing consumers to be idempotent, which is a good thing, right? It makes their code safer. It sounds like a lot more work, but to be honest, you now only have a single code path that they need to test against. You have a series of set events, they need to test against that. You don't need to worry about insert update cases or anything like that. It actually makes their code simpler. All right. Obviously, we've got to be a little bit careful about the size of these events now, right? Because if you have really big set payload events, like set entire user profile, what consumers will end up doing is they'll read the entire user profile from somewhere, update the one little field, and save it again. And of course, if you have a lot of concurrent operations like that, then you can override non-conflicting events, which is a bad thing. And so what we do is we actually have really, really small set events, right? Essentially, the fields you're likely to change together, you put into one event, but otherwise you keep them separate, right? The events are small, they can be cheap. All right, so this is the kind of approach where I guess we eventually evolved to. All right. So the next thing is, okay, well, I've talked about events, I've talked about event streams, right? And I guess, how do they relate? And I guess one of the principles I guess we're trying to push, well, I've been trying to push, is split your event streams as much as you can, parallelize them, okay? And I guess the reason why I said it is there's essentially two schools of thought here. Right? One is you have all events in one big stream, okay? That's really, and if you're coming from a relational world, or coming from a world where this, a different world, this is kind of really safe, right? Because all the events are in place. I can do this. It's not the greatest transactions, but at least we have those constraints right, when we save events. So we have that kind of safety there, right? The problem, obviously, though, is when you have one stream, you have one writer and one reader, right? That's pretty poor in terms of performance, right? And so that's when you really need to start looking at, well, multiple streams, sharding for your throughput, accepting that there is no longer any ordering between event streams, which is not a bad thing. It's actually a good thing for scalability. And I guess we'll talk about it a little bit, but essentially what you end up with is a better latency or availability compromise than you would with a single stream approach. All right, so definitely multiple streams. So I guess the rules for splitting these streams are, firstly, obviously, put independent events on different event streams. If two users want to update their display names, why should they conflict? All right, they're independent. Alice and Bob, they changed the display names, so what? So keep them on separate events. Keep them on separate event streams. There are a couple of ways you can sort of distribute these events. So one by event type. So you might have user events versus group events, for example. And also by unique ID. So you might have per user event stream, so keyed by user ID, for example. So that's the way you can sort of fan out your events quite nicely. Now, I think before you sort of go down that path, though, I guess you do need to, we know, at the end of the day, business systems do have some kind of transactionality required. But you've got to start questioning what transaction do you really need? All right? Just because your current system has transactions everywhere doesn't mean you actually have that as a business requirement. All right? So, for example, for our case, the only thing we really care about is uniqueness, say, of email addresses. And that's it. Every other change, it can be done independently. So we only need transactions on that email address. And that's it. All right? And once we have those requirements and go back to the business and make sure, get those requirements, don't just ask the tech guys, because the tech guys typically will say, well, we need transactions everywhere. Go back and really ask those questions. Then you can start you can sort of then design your model a little bit differently. So I guess one of the things we're doing is more of a hierarchical stream approach. So we have a master stream of, say, email addresses, and then have per user streams for everything else. All right? So that kind of gives us the best of both worlds. Allows you to fan out quite nicely for most changes, but the changes where you do need that kind of transactionality, you can kind of centralize on that one stream. But changes aren't written that often to that one stream, so the performance hit isn't too bad. And one last thing to note is, as with most data models, you actually can change this over time, right? It's not trivial, but if you use things like Scala Days Berlin, it's actually not too hard to be able to split and merge streams later on. All right. So that's splitting event streams, but remember, we have this, no guaranteed order between streams, and that actually has an implication for your downstream consumers. All right, and that really comes down to query views are actually populated eventually, right? Because individual streams are processed independently, so that means two things. One is an individual field in your database table, so imagine a cell in your database table in Postgres, should only be updated by one single event stream, right? That way you can guarantee that you can consistently get the same results each time you replay your events, no matter what order your event streams are replayed in. And in general, you just don't want any foreign key constraints, right? Because there's no guarantee what you're referencing is actually going to be written if that's on another stream, right? And this is a big change, right? To the mindset. We use foreign key constraints, we use indices, those kind of things a lot in the traditional world. But in general, why would we have any constraints on or any uniqueness constraints or those data constraints in our query views? These events represent our data model. Right? They are the data model, right? If you want to prevent anything, you want to prevent things up front, right? There's no point doing it after the horse is bolted, right? And again, this is a big mindset shift. All right, so that's event streams. So next third principle is letting go of transactions and consistency gradually, okay? We're moving into a distributed world. Distributed transactions are bad. I think it's kind of a common theme we've been hearing at this conference and over the last couple of years. But what does it actually really mean for us? And I think it really comes down to really questioning why do we need transactions, right? And I see there's probably two main reasons. So firstly, one is to provide enforce business constraints on write. Okay, you want to say, transactions allow you to transition one consistent model to another, right? And so, things like uniqueness constraints and so forth, that's why we want transactions. We want to confirm that, my model was unique before, or unique emails before. It still has unique emails after I write it to it. I guess the second big reason is, I want other people to see what I've written, right? Otherwise my UI will look a bit funny all the time. That's the kind of the read committed kind of transaction isolation model, all right? That's another reason why people ask for it. And so rewording this is basically talking about write and read consistency, right? But there's always this pesky thing called cap theorem. So who here actually knows cap theorem or understands cap theorem? Excellent. You're beautiful. All right. So I kind of, to explain what I want to get to is, I actually kind of like the PCALC acronym actually for cap theorem. It actually came from a guy called Daniel Abadi, or it's actually his students who came up with this redefinition of, or extension of cap. And the idea is you have the cap bit, so during network partition, so you have sets of nodes that can't talk to each other. You choose between availability and consistency. So if you want full consistency, you obviously can't have it during network partition because nodes can't talk to each other, right? But interestingly, during normal operation, you have a choice now between latency and consistency, right? So if you want a fully consistent model across all your nodes, you need to talk to every single node, right? And that takes time, hence your latency, right? So I guess one of the concerns moving to a distributed system world is, oh, well, are those transactions? I mean, what can I do? It's a big mindset shift, right? And the nice thing about event sourcing is there's this kind of middle ground. And so I guess we've got a couple of solutions we're putting in place. So one is for write consistency. We have this check and set write operation or mode. And on reads, we have this concept of optional forced reads, right? So for check and set writes, the idea is basically all conflicting events are on the same event streams, hence that hierarchical approach. But all we're doing is a check and set loop, right? So the logic in our business layer would be read a view of the data at sequence number X, do my business logic checks, and then try to write using that operation type I showed you earlier, ensure that the stream has not progressed past this point. Okay, and that's kind of your transaction there. So obviously, if you're not careful, this gives you a lot of false positives because if you might have non-conflicting writes, but they've bumped the event stream sequence number up, so you falsely fail and you need to retry. But ironically, if you actually have really small streams, so very few events on each stream, and only conflicting events on a stream, then this actually becomes less of a problem. So you're moving away from a single stream to a multiple stream approach actually helps you, which is a little bit counterintuitive. All right, so that's the write, or write consistency. What about the reads? So the idea is, basically, we need to provide an API for, when someone asks for a query view, they want to say, please give me a query view with sequence number at least X, where X might be the value I might have just written, for example, right? So obviously, when we do that, you do have potentially increased latency, right? This is where your pool model comes in. So most of the time, your events are being pushed to Postgres. But when you have one of these requests, you want to say, well, pull from Dynamo, make sure Postgres is up to date, and then return the result, right? And since increased latency there. So obviously, we don't expose this as a default mode. Okay, it's something people need to ask for to encourage people to think about it. And the other thing we sort of found is make sure you do enforce timed waits as well, because if someone asks for a sequence number a long time in the future, then they'll be waiting there for quite some time. All right, so how do we actually expose this in our API? So we have this concept called a consistency token, right? So if you look at the events, the resources we expose, like a user resource for our REST API, it's actually built up from a number of different event streams. So for example, this Homer user is built up from 2 event streams, all users for, say, their email, and also their user-specific event stream. And so a token for this user, or for this particular Homer user at this particular point in time, is a combination of its sequence numbers from both of those streams. And that's its token. And we return that as part of the E tag for all read and write operations. Okay, and so when consumers, this is opaque to consumers, so they can then pass it back in to, for example, provide conditional writes. We can provide extra header to say, please write only if sequence number X matches. We can also use it for forced query reads, again, series of headers, where you can say, please make sure your sequence number is at least this or exactly this and so forth. And also actually ends up being used a little bit for caching as well, which is kind of nifty. All right. So one of the use cases we use this for is say you want to add a user, then you want to add a group, then you want to add that user to that group. Now, obviously, that third operation, you need both the user and the group to exist, right? So let's have a look through this sequence diagram and see how that works. So obviously, the first thing is the client tries to save that user, gets back that user token, the same as that Homer token I showed you earlier. You then try to save a group, get a group token back. Now, the key thing here is this add user to group operation passes through both of those opaque tokens back to the server, right, with appropriate headers. And that's when the actual server then forces query views to be updated to sequence numbers, then does its business logic check, then does its check and set writes, and when that works, then you can return an updated token itself. So this is, I guess we don't actually see this very often, but there are some cases where you need this kind of capability, and and that's at least event sourcing gives us the ability to do that. All right. So the last principle I want to talk about is I call it 3.5 because this is something we're not doing yet, but it's something we want to get to, right? And that's moving away from this upfront transaction, upfront check and set writes to conflict resolution, right? And the idea is, well, we have all conflicting events on the same event stream already. So in theory, if we have the same resolution algorithm defined on all of our query nodes, then we should have consistent views generated by each query node independently, right? There's no consensus required there. So things like you might use last write wins as a worst case, or ideally we want to use these CRDTs, so convergent or commutative replicated data types, CRDTs. Okay, and the nice thing about that is you don't no longer have these transaction issues. You don't have that check and set write false positives anymore. You make your query views a lot more resilient because events may come out of order. It's okay. You can just apply them. Eventually, they'll get consistent. You can, with a little bit of care in the way we're structuring the key structures correctly, you can actually get multi-region writes working pretty nicely too. Obviously, there are potential glitches because during that resolution process, you might have different answers between different nodes. And I guess the biggest kicker for us, which is why we haven't really looked at it too much yet, is all our query nodes essentially to implement the same algorithm, right? And if you use CRDTs, it's not straightforward yet. It will eventually get there, but it's not straightforward yet. All right, so that's a bit of a whirlwind tour of, I guess, what we've been doing. So I guess let's take a step back and go through some of the key takeaways. All right. So the first big one is, I'd say, is start small and challenge everything. All right. So we talked about, the identity platform, users, groups, memberships. In retrospect, we thought that was a pretty small component of the system. In retrospect, it actually was too big. Right. We should have started even smaller than that. All right. And that would allow us, I guess, challenge more of those requirements. I guess rather than focus on understanding the full model, but allow us to focus on small bits and challenge what those requirements were to begin with, right? And also another aspect around challenging everything is it's really important to get the right team to do this, right? So you need to get the team who are willing to challenge the status quo and ask, why do we have transactions? What are the actual underlying business requirements, right? So that's really, really important. Second, the incremental architecture approach actually worked really well for us. Okay, so if we went to our bosses and said, we're doing event sourcing and CQRS from the beginning, look, I wouldn't be here, right? So, but because we started with event sourcing first, we started building, spiking that out first, and as people were building the production version of it, then we started spiking out the CQRS bits, the event source, the event bus bits, and so forth. And I guess we were able to show people how we were getting it, and bringing people along for the ride. I think that helped, I guess, give us some confidence that we knew what we were doing. In terms of design, there's the three key sort of takeaways. So firstly, thinking events as an API. Okay, small identified events, set payloads, really small, as small as you can. All right. Event streams, split streams as much as possible. Don't be suckered into everything in one single event stream means transactions. Don't get sucked into that. And in general, I think because we're moving to this whole distributed system world, we really need to start looking at weekend transactions and eventual consistency. We just need to get comfortable with it, okay? Two things I want to leave you with. So firstly, Martin Fowler came to Sydney a little while ago, and he was giving me a talk on event sourcing. So it's like a pet topic of mine. It's like, yes. And he said, this is me loosely paraphrasing him, we as an industry should be using event sourcing more than we do. All right? It's really powerful, okay? You don't have to use it everywhere, but using the small bits of your core parts of your system can give you massive benefits, right? And secondly, I'll give you a couple of links. So we've open sourced our event source library, so you can have a look at that there. So we're still actively developing that. The Dynamo bits of it obviously rely on our AWS Scala library, which is essentially a functional wrapper around the AWS SDK. So have a look at that as well. And on that note, thank you for your time, and do you have any questions? Yep. I'll just repeat the question. Sorry.
Yeah, you talked a little bit about the transactions, and I guess in some domains you sort of want the user to do something that, for example, if a manager approves a budget, then he does not mean to approve the budget if someone else added something to the budget since he read it. So, yeah, and then your solution here is sort of to cut up the event streams, but can you maybe go into a little more detail on how that solves the problem?
Yeah, so it's interesting. Yeah, so I guess a lot of our transactions are very short-lived, right? So on longer-term transactions, I probably end up putting on top of, like as an extra layer on top of, like a workflow system on top of it, right? So rather than using event sourcing transaction directly for that. So you might use the events, I don't know if you do even need to use event source transactions for, you'd probably store the individual data elements. So each phase of your workflow, you'd have event source data. Whether or not you need transactions for each of those, maybe, maybe not. But the overarching one, yeah, the lock for that, for example, yeah, that might well be an individual stream of, please make sure, you might have a master stream of workflow steps or something, that's where you lock on essentially to give that capability. Something like that would work.
Hello?
Hello? Yep.
Will you consider use a persistent actor for the event sourcing?
I knew that was going to come up. So the thing with Akka and stuff, Akka doesn't really fit in terms of the way we deploy our code, and also the way, so we deploy our code on, our apps are basically stateless. We use 12-factor app style, so having clusters and stuff wasn't really out of the question. So that, and I guess the second part of that is the way we code, we're kind of like, we're very functional of our code, so the way Akka and the Akka model doesn't really gel the way we code. You think of it, we use Scala, but more like the Haskell way. Okay, so we sequence things with futures and stuff like that. So rather having, so that's the reason why we didn't really consider it. And plus, I guess, yeah, we didn't. For a lot of our application, they're really simple, right? So we didn't really want to bring in big new frameworks just for essentially a fairly small component like this. Cool. Any other questions?
On the write store and the read store, when changes, the changes coming into the write store are coming in very quickly.
Yep.
Have you run into a problem where the read store can't keep up?
Not yet, I guess. So I guess it's interesting, right? You mentioned, so for our writes are a much lower level than our reads, right? Because you imagine that you don't change your user profile that often, right? You add new users a lot, sure. So we don't really have that problem. So I guess so one of the things we would probably look at doing is essentially batching up events when we on our read side. So at the moment we're doing pretty dumb, essentially, for each event do some statements, right? We can actually do a lot more smarter and batch up events and write them out. Well, essentially when you read from Kinesis, you poll every once a second, right? And you get a whole bunch of up to 100 events, I think it is. And you can process all those in one big batch to get some more performance out of it. But I mean, to be honest, we haven't hit that problem just yet. So we have lots of other things we can tune before that. Cool. Any other questions? Oh, yeah, I see your hand.
This whole event sourcing stuff sounds very nice, but when would you apply it and when would you not apply it? Because it's probably not a silver bullet.
It's a good question. I guess I'm kind of leaning more towards when would I not apply it? At least think about it, because you look a lot, it comes down to your business use case, right? So whenever you start doing things like, I want history of data, I want audit trails, those kind of things, it becomes a very natural fit. Admittedly, yeah, look, for a lot of simple CRUD style applications, look, to be honest, just stick it into Dynamo directly or something, right? You don't need event sourcing. But I think for the core parts of your system, I think that's probably where you start looking at, because these are things you don't want to change very often, and you do want that safety and flexibility. So that's where I'd start looking at event sourcing. Cool. Anything else? All right. Oh, nice. Ooh, a couple more.
Hi. I'm having a hard time trying to understand why the events need to be that small and how to decompose that from a normal REST API with normal patches, puts, and everything down to small events, and what's the benefit that actually brings?
Sure.
Could you elaborate a bit more?
Yeah,
please?
sure. So I guess first bit is using set events, set payload style events. So to encourage idempotent processing is, I guess, one part. The reason why you don't want to have big events is, if you say, imagine I want to have, rather than having set user email and set user display name small events, you have a set user profile, which includes email, username, address, company, all those kind of things in one big payload, right? The only way you can ever set, the only way a consumer or client can ever write that event is to have the entire payload, right? Because a set event is the entire thing. And so, therefore, to get the entire payload, you essentially have to read a version of it from somewhere, like a query store from Postgres, change the one little field, and then save the entire payload again. All right, so that's the normal operation. Now, if you imagine you have multiple writers now, concurrent writers, so you've got two people, one person, or two clients changing that same person's, one person's email and the same person's display name. They read the same view from data from Postgres. One of them changes the email, one of them changes the display name. Both of those events get saved as events. Only one of those, so the one, depending on which one comes last, is the one that will win, right? So if the one with the email change comes last, its payload includes the old display name, right? So that means that overwrites the change from the other person's or the other client's display name change. And that's what I mean by non-conflicting writes can actually get overwritten because you're essentially using an old version of data. Now you can kind of prevent that using check and sec transactions and the like, but then again, then you run the problem of having transactions and so forth, right? So you have to find that balance. That's why I guess we've found that having really small events, and that to be honest, they line up more with the way you would model, at least for us, the way we'd model our domain events anyway. They're pretty small, so that's the reason why we sort of have it trended towards that. Does that kind of answer your question? If not, I can come and we can have a chat afterwards and we can draw it out. Yep, sure. I think.
Why are you still using databases like Postgres?
That was an interesting one, actually. We got mandates to use that, so it's not my choice. Part of the reason is, look, people are comfortable with Postgres, right? You have a SQL database. It's just, and that's why having the right team is really important because, and people are comfortable with certain things, right? And Postgres is one of those things people are comfortable with. It wasn't, technically, I don't think it was not necessary, but, there are, not all design decisions are technical, unfortunately. So that was one of those that wasn't.
But why do you still need them if you have event sourcing? That was my question.
So you may still want to have a cache of data somewhere. Whether or not it is in Postgres or we were actually going to use Redis, for example. That's probably a more effective way of doing it. It's fast, it's cheap, and it can replicate easier. You don't need Postgres or SQL. I completely agree. But well, you may choose to do it for some query capabilities, right? So you might want to say, I want to write these tables out and I want to use SQL to query things. Whether or not you use Postgres versus Elasticsearch for that is not a question. But again, some of those technical decisions are because of comfort, because of experience and so forth. So it's a bit of a mix of, of a few requirements there. Yep, I think there's a gentleman. You want to help?
How do you handle updates of event model?
Good question.
Event model changes over
Yep.
time, and
Yep.
that can be difficult because you have
Yep.
history in a different way. The events,
Yep.
the former events are different from the ways you use now or in future.
Yep, good question. So I think we came up with about 6 or 7 different types of changes. So the way you, fundamentally is you version the events, right? So each payload has a version number, and over time you build up, so we basically have a JSON and codec, right? And we basically have built in that, the ability to delegate to the appropriate codec to decode existing old versions of JSON to the latest version. That's fundamentally how we change it. It gets more interesting when we start saying, well, I want to move events around between streams and so forth. And again, with some care, you can start saying, well, I want to read from multiple streams and process events from multiple streams, and I guess or join from multiple streams. So you have the kind of ability to do that to allow you to handle that. Now, I guess next question is, do you have that long term? And what you could do as an offline operation is rewrite all your old events to your latest version over time, but that's like an optional thing, I guess, in a sense. All right, so that's a kind of an optimization to avoid having to keep all the crud of different version processing in your code over time. So yeah, so it's not an easy thing to do, but it's definitely, and definitely doable. It made it a lot easier when you use things like Scala Days Stream and those concepts. I think there was, where was, okay, yep.
Just one more question.
Yep.
When did you start researching the things, and when do you plan to go in production?
Okay, so so the basic event sourcing stuff we actually have in production. It's been in production for about 18 months. So it backs actually a lot of our Jira attachments actually in cloud. This particular system we've been building for a little longer than I'd hope. It's probably about a year about now. We should be. I don't want to say when we're going to in production because you never know, but it will be this year. I mean, to be honest, most of this stuff has actually kind of been. This represents one part of production, I guess. That's the challenge, right? A lot of it is then how do you actually get things in production? So, sometime this year hopefully no one will notice because it will just be out there and you guys will just use our Atlassian products and it will just work and you just won't notice anything. Cool. Any other questions? If not, I have time for one more and then if not, I'll be around all day. So yeah, come hassle me as well. All right, cool. Thanks, guys.